In this video, we're going to have a tiny review, and then we're going to continue looking at velocity and time and distance under constant acceleration. Just the most microscopic review, we talked about a distance is measured in meters. Velocity is how far you go per unit time. Velocity would be in meters per second. That's how fast you're going. The change in distance per unit time. And acceleration does that again. Acceleration is the change in velocity over the change in time. How fast is your speed changing as the clock ticks? That's your acceleration. And that's meters per second. And that's meters per second squared, as we know. And then we know that the distance you travel is the speed you're going times how long you've been traveling. The speed you have is the acceleration with which your speed is increasing times how long your speed has been increasing under that acceleration, okay? And the distance that you travel under a constant acceleration is 1/2 a t squared, and that's what we talked about last time. Let's see if I can use Notability to draw a box. Nope, wouldn't draw me a box. But we're going to move on from there. There's one more thing that we determined also that we're going to look at a little differently. We figured out that if you drop a ball from a certain height and it hits the ground and it travels a certain distance d under a certain acceleration a, that the velocity when the ball hits is the square root of 2 times the acceleration times the distance that it fell. And we'll come back to that. But the first thing we're going to do is we're going to take a look at a related problem. Well, last time we dropped a ball from a building and it went a distance d and it hit the ground. And this time we're going to let the ball travel the same path, but this time we're not going to just drop it with a starting velocity of 0. We're going to throw it down. So at time 0, the ball has a certain velocity. We'll call it v sub 0. You've thrown it down, and so it's going to start with that velocity, and it's going to accelerate as it did in the previous example. Now, there is an equation that in the Physics 1 AP test they'll give you a whole bunch of equations, and one of those equations says that the distance something travels is its initial velocity times how long it's traveled plus our 1/2 at squared. If there is an acceleration, then this participates in the distance it traveled. If there was an initial velocity, then that participates. If you have both an initial velocity and an acceleration, as we do here, then this is the equation that will show how far it travels. Now, let's take a look at how we got to that. Okay, so here is our velocity time graph. This is time, and this is velocity. Now, since we threw the ball down, we're not going to have a velocity that starts at 0 and goes up with the slope that is equal to the acceleration as we did in the previous example. No, sir. Because this time, we're starting out with a certain velocity, v sub 0, at time 0. And starting at time 0, the particle is going to accelerate, still with the slope equals a. It's going to accelerate starting at v sub 0. We still have the situation that the area underneath the velocity time graph is the distance that the particle traveled. Okay? And let's call this t sub 1. That's where the ball hits the ground, or that's where the ball is done traveling after its acceleration. So how do we figure out this equation right here based on our velocity time curve? Well, let's take a look. Before, we had the situation where we were figuring out the area of a triangle because a ball started with a velocity of 0 and it went up to a velocity that was the acceleration times the time that it had been traveling. And that's how we computed the distances 1/2 at squared. This time, the velocity increase that we have from the acceleration is still the acceleration times the time that it was traveling, but we started out with a certain velocity here. So we have this triangle of 1/2 at squared, but we also have this rectangle here. The fact that the ball started with a certain velocity, v sub 0, that velocity participated in giving the ball distance throughout the entire t1 time that it traveled. Okay? So this is v0. This right here is the speed where it ends, v1. And v1 equals v sub 0 plus the additional velocity that it got because of the acceleration, which is a times t1. So v1 is larger than v0. We can say v1 minus v0 equals the acceleration times t1. So what is the total distance that this thing traveled? Well, we have the rectangle down here. That's if you're traveling at a certain velocity for a certain amount of time. Distance equals velocity times time, right? And then in addition to that, we have the triangle above. We have the 1/2 at squared for that triangle, okay? So it's plus 1/2 times the acceleration times the time squared. And oh, look, that's exactly the equation that we wanted to find out. So now, if we want to find the amount of time that it took for a ball to go from the top of the building to the ground, and we know that we started with a certain initial velocity, this is the equation that we use. And we'll discover that for a given distance, the time obviously will be less because we threw the ball down there. Does that make sense to you? Now, we're going to talk about another equation that you are going to see on the list of equations that you're given. It's not used as often, but here it is. And this equation says v squared equals v initial squared plus 2ad. Okay? And what is that? That's an equation about acceleration and speed and distance, but they pulled the time factor out of it. And here's how they did that. Let's take a ball that is going to undergo an acceleration. It's going to start with a certain initial velocity. It's going to speed up with a certain acceleration. This is time. Okay? Here's t sub 1. Here's the velocity where it ends. This is v sub 1. And the area underneath this curve is the total distance that it traveled. Okay? Well, this total distance that it traveled is a trapezoid. It has parallel sides that are unequal in length. So what is the area underneath the trapezoid? Well, let's actually do it. if we have a trapezoid like this, the area underneath the trapezoid is the base times the average of the two heights. If this is C and this is D, the area equals B times C plus D over 2. And even geometrically you can see that. So that if this is the average of C and D, then this area right here is the same as the area of the entire trapezoid. So what is the area underneath this diagram where a ball started out with a certain velocity and it underwent a constant acceleration for a certain amount of time? Well, the area of that trapezoid equals the time, which is the base, times v sub 1 plus v sub 0 over 2, right? And that equals the distance that the ball traveled. But we still have time here, and the point of this is to pull the t out of this equation. So let's see what's going on. We know that the speed increase during time, which is v1 minus v sub 0, that's how much the speed increased over the time of this travel. That equals the acceleration of the ball times the time that it was traveling, right? So let's work with that. Once again, back to our simple 8th grade algebra. Let's divide both sides by a, and we'll say v1 minus v0, which is the increase in speed, divided by the acceleration, equals the time it was traveling. That's no different from if you have a particle that starts at rest and accelerates, you would say that its velocity is the acceleration times the time that it was traveling. So divide both of those by a. You can say the velocity divided by the acceleration equals the time, right? Okay, so now we have an expression for t, and let's plug it in up here. So we're going to say the area under the curve, which we know is the distance that the ball traveled, right, equals t, which is v1 minus v sub 0 over a, times v1 plus v0 over 2, and there we go. So let's work this out. We of course know from algebra that x plus y times x minus y equals x squared minus y squared, right? So this expression here is v1 squared minus v0 squared, right? All over 2a, and that equals d. Let's multiply both sides by 2a. v1 squared minus v0 squared equals 2ad. Okay? And now the way they like to do it is to add v sub 0 to both sides. So we're going to say v1 equals v sub 0. v1 squared equals v sub 0 squared plus 2ad. And that's our equation. It says that, let's rewrite it a little bit different. The new velocity squared equals the old velocity squared plus 2 times the acceleration that changed the velocity times the distance that the particle traveled while the acceleration was acting on it. Now look at this. What if we use this equation of ours and we say that the original velocity, the old velocity, was 0? Okay? Let's say that we dropped a ball off of a building and the old velocity was 0 because we didn't throw it down, we just left it there. Okay? So the old velocity is 0, And we're going to say the new velocity squared after traveling a distance d under an acceleration a equals 0 plus 2ad, which equals 2ad. And now let's take the square root. Velocity equals the square root of 2ad. And that's exactly what we figured out at the end of the last video. Okay, and there are times when this will be an equation that's easier to use than trying to figure out how long a ball was dropping or something like that. So that's it for this video. For this one, as well as any other video, please contact me with corrections or comments or any suggestions for improving these videos. Greatly appreciated.